Hey guys, so today we're going to talk about electron configuration. So what scientists have done is they have figured out where they can find an electron. So if you take an arbitrary hydrogen atom, it has one electron, but we can't say that the electron's going to be here, or we can't say it's going to be here at any given time. So what scientists have done is they have measured where the electron locates itself. And they have noticed that in a hydrogen atom, it locates itself in a sphere, and it is anywhere in the sphere at about 90% of the time. The other 10% of the time, it's outside of the sphere. The sphere is really important because it helps us know where the electron spends most of its time so we can study the bonding of a hydrogen atom. So the way we're going to write our electron configurations is easy. I'm going to show you my periodic table of elements, and this one is already split into the different shaped orbitals. So the blue columns here are s orbitals. And an s orbital is exactly like it sounds, it's a sphere. And these yellow elements right here are p orbitals. And the p orbitals look something like this. And then here's your fluorine atom, let's say. And they look like this. So the electron spends 90% of its time in either this side or this side. The d orbitals are here, and the f orbitals are these green ones. And they get a little more complicated, so we won't be going into those, but maybe in a future video. So for our first example, we're going to look at the helium atom. And the helium atom has 2 electrons. And it has 2 valence electrons. If you don't know anything about valence electrons, look at the previous video, which is the electron dot video, and it'll show you how helium works. So helium can also be written way over here beside hydrogen for our purposes. All right? Because helium has 2 electrons. So to count its electron configuration, we see the group it's in. It's in group 1. So it's 1, and it's in the blue side, so it's S, and it has 2 electrons, so like that. Now, the 1s orbital can only hold 2 electrons, all right? So when you draw out a helium atom, it has 2 electrons that spend its time in the 1s orbital. So that's a 1s2 configuration. Let's pick something a little harder. How about fluorine? All right, a fluorine atom has 9 valence electrons. So let's count. We have 1s1, 1s2. So let's go back and write that on our paper. So fluorine has 1s2, so it has 2 electrons in the first s shell. And then we come down here, and we see that the next shell is 2s2. So we go back and write that here. 2s2, it has 2 electrons in that shell. We come back to the table, and we see in row 2, it's now in the p orbitals, and we have 1, 2, 3, 4, 5 electrons in the p orbital. So we're going to go 2, because it was in row 2, p, because it was a yellow element, and it had 5 electrons there. Now, fluorine had 9 electrons in total, like we said, and how we can know if we did this right is that these little numbers should add up right. So add up to 9. So there's 2 electrons here, 2 here, and 5 here. And that equals 9. So that means we've accounted for all the electrons in fluorine. So I'll draw a picture of this for you so you can just see how it looks. All right. So fluorine, its nucleus is in the center right here. And it has 2 electrons floating in its 1s shell. And then it has 2 more electrons floating in its 2s shell. And the 2s shell is bigger because it's further down on the periodic table. And then it has 5 electrons in its 2p shells. Now 2p's are hard to see. 1p shell looks like this, and has 2 electrons in here. And the next p-shell looks like this, has 2 electrons in here. Alright, and the third p-shell only has 1 electron because we only have 5, but we have room for 6. So, but that one p-shell is coming out towards you. And so I'm going to draw it like this, and then there's one behind it. Alright, and it's coming out towards you and then back into your screen. So that p orbital is coming out towards you. It has 1 electron in it. So we've counted for 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. Hopefully that helps you with electron configuration, and stay tuned.
Hello again. Today we are going to discuss the mole concept. Atoms are so small. To count out individual atoms would take forever. So to make the counting a little easier, chemists work with the unit of moles. The mole is the SI unit for 6.022 times 10 to the 23 particles. Now that is a really, really large number. Atoms are so small that in the lab or at home we really work with trillions of atoms or molecules at a time. However, we may now convert from extremely large number of atoms to just the number of moles of atoms or molecules. So I have an example here. How many moles are there in 1.204 times 10 to the 24 atoms of copper? So you have 1.204 times 10 to the 24 atoms of copper. And that you can divide by Avogadro's number, which is this. So divide by 6.022 times 10 to the 23. And the units for that are atoms per mole. So you use your calculator to divide those two numbers, and the atoms are going to cancel. So you get 1.999 moles of copper. Hopefully that helped you out with converting atoms to moles.